In what we've done so far with nonlinear systems, we've seen how to linearize around equilibria, and then just like linear systems, determine stability or instability from that linearization, and then stitch together these pictures to get an overall sense of stability or instability of the nonlinear system. And then in the last video, we talked about the limit cycle and how that is really a generalization of an equilibrium. And we've seen how it can be both stable or unstable, essentially attracting trajectories or repelling them. And so we're going to bring this together, these ideas together, to talk about stability of nonlinear systems in general. And so to do that, we're going to talk about one last piece, which is the notion of a positively invariant set. And so the idea of this is that if a state trajectory, like this one here, enters a region, M, and it stays in that region for all time, all future time, then that means that there must be something kind of quote unquote trapping that state trajectory. And so the result is that if you have this positively invariant set of a nonlinear system, that there either must be an equilibrium inside that. So for example, a stable equilibrium that's attracting all those trajectories, a sink of some sort, or it could be a stable periodic orbit that's trapping those. And so this Poincaré-Bendixson theorem gives us a tool to define these positively invariant sets to help to determine the stability of nonlinear systems for more complex geometries. But the nice thing is we can pick this M however we want if we can show that it's positively invariant. And so now we'll see an example of how that works. The goal of this example is to demonstrate this idea of a positively invariant set, and then how we can leverage all of our tools about stability to determine stability of the overall system. And so we're going to take this rather complicated system of differential equations that is nonlinear. And again, I'll let you pause the video to confirm to yourself that the origin is the equilibrium point in this case. And the Jacobian around that equilibrium point is given by this matrix A. And again, also, that if we calculate the eigenvalues of this matrix, we get 1 plus or minus I, which makes it unstable because the real part is positive, and complex, which makes that it is a focus or a spiral. And so what we said is that if we can define a positively invariant set, that we can say something about stability, and in particular, the existence of an equilibrium or possibly a limit cycle. And so what we're going to do is we're going to devise some clever sets to help us do that. And so if you think about this set, x1 squared plus x2 squared, for different values of that function, so for different values r squared, that defines a circle of radius r. And what we're going to do then is we're going to evaluate how the F dynamics point along either inside or outside of that circle. To determine that, what we're going to do is we're going to define, so the gradient of this function c is simply just the partial of c with respect to x1 and the partial of c with respect to x2. So this function, this gradient is a vector, and the first element is 2x1 and the second element is 2x2. And depending on, so obviously this depends on what x1 and x2 are, and so because this is the gradient of this function, it's going to point in the direction of greatest change, which means that it's pointing radially outward. And so in blue on this figure, I've shown how the gradient of this function c is pointing radially outward no matter what circle we've chosen. So now by taking this vector, this gradient vector, which essentially expresses perfectly outward trajectories. And taking the dot product of that with the vector field f, we're going to get a quantification of whether that's pointing along the outward direction, which would be a positive number, or pointing in to the inside of that circle, which would be some negative number. So as close as it gets to 0, so if it's close to 0, then that means that if, for example, gradient of c dotted with f points directly tangent to the circle, that's in the case where this dot product would be 0. Or if it's pointing in this other direction, that's tangent. But as long as it's pointing inside, you're going to have a negative number. If it's pointing outside, then you're pointing along the gradient, then you're going to get a positive number. And so if we plug in f1 and f2 here, so this is f2 and this is f1, if we plug those in and do some simplification, we get down to this expression. And the convenient thing about this is that we have these expressions, x1 squared plus x2 squared, x1 squared plus x2 squared, which is exactly this c function. And so that allows us very easily to determine whether or not it's going to be inside or outside. And so we can now take two different circles. So let's take an outer circle of R2. So R is equal to 2 units. So if it's equal to 2 units, then that means that that C is going to be R squared. So it's going to be 4. You'll have 4 for this value, and you'll have 1 minus 4 for this value. So that will give us a negative number. So it means that outside this large circle, or at this large circle, it's going to be pointing into the middle of the circle. So it's not necessarily pointing directly straight in, but it's pointing at least somewhat in. And so this is an example of one that's not pointing directly in, but at least it's still pointing inside the circle. If we take a smaller circle at r is equal to 1/2, then this becomes 1/2 squared, which is a quarter, and then this becomes 1/2 squared, which is a quarter. So 1 minus a quarter is 3/4. So that means that both of these are now positive, which means that this overall dot product is now positive. And that tells us that the dot product is pointing outward from that ellipsoid. All right, so what does that tell us? That tells us that this annulus, so this donut here, is actually positively invariant. That means that trajectories, if they're on this circle, they go inside. And if they're on this circle, they go outside. And so that means that if they go inside from this circle and outside from this circle, that means that none of the trajectories in here can go into the center of the donut or out of the outside of the donut. So neither of those are possible, which means that that annulus is positively invariant. And so that implies that there must be a limit cycle or an equilibrium point inside that annulus. But since we already know that the only equilibrium point is right here at the origin, that means that there must be a limit cycle for this particular system. And now to finalize our discussion about stability, we'll finally define stability in a rigorous way. And so what we kind of colloquially think of as stable is actually more like asymptotically stable. And so stable is simply just the idea that given some initial condition within some ball, that we can define some other ball for which that state never leaves that region. So this is again some notion of positive invariance, and this idea that you have some sort of outer bound here so that you know that your state can't leave that as long as you start small enough. And so again, this doesn't mean that it's actually converging towards any particular value, the origin or anything else. It simply just means that it's contained in this positively invariant set. Again, what we often think of as stability is what's actually called asymptotic stability. And this is the idea that as the state, as time goes off to infinity, as time goes larger and larger, the state keeps getting smaller and smaller, and in the limit, the state goes to 0. We can add a qualifier called globally, which says that all initial conditions are asymptotically stable. So all initial conditions go to the origin. And linear systems only have one equilibrium, which means that any type of stability that they do have is actually global. And so that's an example where if you only have that one equilibrium and it is asymptotically stable, that it is also globally asymptotically stable. And so another stronger form of stability is called exponential stability. And this is the idea that that because it's stable, it means it's going to be diminishing in value just like this. But now what we're going to do is we're going to say something about the rate. So whatever the initial norm, the side, the distance away that the initial condition is, that distance is going to decrease at least as fast or faster than some exponential rate, which is characterized by lambda. And this looks very much like the type of solutions that we had for linear systems. And for that reason, asymptotic stability for linear systems implies exponential stability because the solutions just look like these exponents. For nonlinear systems, stability becomes a little bit more complicated. But again, remember that we can determine the local stability based on the linearized dynamics around different equilibrium x star. And so we can talk about a specific equilibria in terms of nonlinear systems. And so if all of the eigenvalues of the linearization have negative real part, then we can say that that linearization is exponentially stable or locally. So locally around that equilibrium, it is exponentially stable. We can also say that if any eigenvalue is positive, then that there's definitely going to be a direction where the trajectories leave and grow unboundedly. And so that means that that x star is unstable. So for any positive eigenvalue, that equilibrium is certainly unstable. And then if any eigenvalue of A has zero real part, then it depends. So it can't be exponentially stable, but it could be stable, so its trajectories could stay contained. Or it's also possible that, that it is asymptotically stable, so things converge. Or it's also possible that it's unstable. And so you can develop examples for all of those different cases. So this will give you stability of each equilibrium. It's very similar to what happens for linear systems, but now that we have to stitch these together into a kind of this global idea, this tells us something about a little bit more about these linearized equilibria for the nonlinear system. And then we would use other tools such as positively invariant sets to determine stability of the overall system. And then in the next video, we'll talk about a more advanced way to determine stability all together and not relying on linearizations. And so we'll see that in the next video.